So in this video, I briefly give you some notes on the properties of eigenvalues and eigenvectors, and please recall the definition of the eigenvalue and eigenvector. I hope that you have watched the last video already when we did some computations about the eigenvalues lambda and the eigenvectors v based on different matrix. And just look at the first note. Let's say now A actually has size n by n. And I claim that every time when you solve for the eigenvalue, you basically have to look at certain polynomial equations in lambda. And this equation is usually a polynomial in lambda of degree n. It's always like this. It's basically a property of the determinant. And this n comes from the number of rows or the number of columns of the square matrix A. And of course, because the polynomial has degree n, it means we basically have at most n real eigenvalues. It can be less. It depends on the system, right? And also sometimes the solutions can be repeated as a repeated root. And the other fact is more important. The fact is that for each solution you found by looking at this polynomial equation in lambda, it has at least one eigenvector for each eigenvalue. And the fact is that each eigenvector associated to different eigenvalues, they must be linearly independent to each other. And let me put it here. So basically that's the fact here. So please look at this second fact. It is actually more important. And then we can look at the second note here. So let's say now you actually have an upper or lower triangular matrix, and in this example A, I'm just giving you an upper triangular matrix. And if you try to find the eigenvalue of such an upper triangular matrix, of course we have to solve for such an equation. And please recall how's the determinant formula like. And please look at this matrix now. This matrix is still upper triangular, right? Because subtracting the matrix A by the lambda times identity. So lambda identity is a matrix like this. So after the subtraction of lambda at the diagonal spot, this matrix A minus lambda I is still a upper triangular matrix, right? The only change is along the diagonal, something like that. You see the shape is still unchanged. And if you recall the special fact about finding the determinant of such an upper triangular matrix, you remember that no matter the size of the matrix A, even if it is very big, the fact is for determinant of such a shape of the matrix, we just have to multiply the diagonal like this. And you can see I'm assuming A to have size n by n. That's why it's from A11 up to ANN. And now it's basically a polynomial in degree n for lambda. And you have to set it 0, right? And it basically means the possible eigenvalues are basically just all the diagonal entries, right? And it becomes easy simply because the matrix A is of a special shape, which is upper triangular. Let me write the conclusion down here. So please look at my conclusion in the black box here. For such a special matrix of such a shape, we can simply write the eigenvalues down just by looking at the diagonal entries. So it's quite easy actually for such a matrix. And let's look at the next note. So let's say now you already know the eigenvalue and the eigenvector for certain matrix A. I would like to do some matrix operations on A square. And I would like to determine the corresponding eigenvalues and eigenvectors of A square as a matrix. And let's try to apply this matrix to the column vector V. Can you do some matrix manipulations here? You see the fact is that if you multiply the second copy of A to the column vector V, we understand that it can be written as lambda times the column vector V, right? And because lambda is a constant, we can pull it out. It doesn't affect our matrix equation for the constant to be pulled out. And now please look at this fact. This one can be changed by using this matrix equation again. If inside the bracket, we actually have lambda times column vector V, right? So altogether, we have lambda squared times column vector V. So what does it mean? So the conclusion is that you have such an equation for the matrix A square. For the matrix A square, we actually have the eigenvalue lambda square, and for such an eigenvalue, we actually have the eigenvector V. You see the eigenvector V is the same as the one you found in the matrix A already, but of course the eigenvalue is not the same, it's lambda square actually. And you can actually do an induction on this process. The conclusion here is that actually if you take the n to the power n, basically I'm saying you do the matrix multiplication n times, like this. And we understand automatically that it must have the eigenvalue lambda to the power n, and the corresponding eigenvector is v. And that's the third note we have, and that's the end of this video.